Hi everyone, welcome back to the Vent Lab for our next lab session, and this is the Ventilation Survey Lab. This is going to be a fairly quick demonstration, and it should serve to tie together your modeling work in VNet PC, along with the other analytical and lab skills that you've learned this semester. The Ventilation Survey provides you with some of the information you would need to construct and then validate a software model, and then once you have a good software model, you can experiment with ventilation optimization and also plan for future expansion in your mind. The basic principle in a ventilation survey is that the pressure generated by your fans will equal the summation of the pressure drops in your mine, drifts, shafts, and other airways, as air flows into and then out of the mine, usually with the help of one or more fans. If you recall back to the fan test stand lab session, we saw that the operating point of a fan expresses the balance between the pressure generated by the fan versus the pressure drop in the system or network to which the fan is delivering air. So as a refresher, here is a fan curve. So flow rate Q increasing to the right, pressure P increasing as we go up. Typically you'll have maximum flow rate at minimum pressure and vice versa. And more review. Here again is a system resistance curve. And again, recall that this is a plot of P equals RQ squared. So flow rate increasing to the right, pressure increasing as we go up. And as the flow rate increases in the airway, the pressure required to develop that flow rate has to increase exponentially. So that's P equals RQ squared. And the two curves intersect at the operating point for that fan and that system. Okay, so fan performance curve, airway resistance curve. So where they meet, the fan will develop that much pressure and supply that much flow Q. Okay, the same principle applies to a mine as a whole. However, as you well know, once you get more than a few interconnections between airways, it becomes very challenging to calculate the system resistance without using a software model. Now, thinking back to our second lab session, the anemometer traverse lab, you'll recall that we set up fans in the doorway at the end of the LME first floor hall, and we established a fairly decent airflow using the hall as our airway. We have the same setup for this lab session. However, instead of measuring the velocity for the purpose of determining the flow rate Q, as we did in the traverse lab, in this lab session we are going to look at the summation of pressure drops in the airway versus the pressure generated by the fans. As a professional ventilation engineer, you would use both sets of data, P and Q, in the development of your software model. The fans are set up in a plywood panel in the doorway out to the loading dock, and they're again configured to exhaust air from the hallway out to the loading dock. So this is another example of a suction system, similar to the calibration wind tunnel we used in the very first lab, the friction factor wind tunnel, and the fan test stand. And then just to remind you, the airflow demonstration unit and the bag line pressure drop survey were both pressurized systems. Okay? So here's a diagram that Professor Kosis has drawn up for the lab handout for this lab. A schematic of the first floor hallway of LME. Here are the glass doors out to the breezeway. You might remember doing the anemometer traverse there, so those are propped open. The fans are at the opposite end of the hallway, blowing the air out to the loading dock, and so the air is just going to flow around the hallway. Here's the vent lab, and exhaust out to the loading dock. So fairly straightforward. The measurements that we are going to take will be delta total pressure measurements with pitot tubes. This will be very similar to some of the measurements we recorded in the friction factor wind tunnel lab session to calculate Atkinson's friction factor K. So we have two tripods that are set up with pitot tubes. We'll connect the total pressure taps on each pitot tube to a manometer, same type that we've been using throughout the semester. And the manometer is going to be set up to read the pressure in pascals instead of inches of water, it's a little more sensitive that way. We'll have a single length of tubing from each pitot tube connected to the manometer, with the upstream pitot tube connected to the positive pressure port and the downstream pitot tube connected to the negative pressure port. Again, remembering air flows from high pressure to low pressure. And both pitot tubes need to face into the flow. This is normally something that we would have you guys doing as a lab exercise. You would have two people holding pitot tubes, just holding them, and we'd record the delta pressure measurements. But in this day of social distancing and hand sanitizing, it's just going to be me using the tripods. Okay? So we're going to go around the airway in the direction of the air facing into the airflow. We'll record the delta total pressure values as we go around, and then finally we'll measure the pressure increase across the fans. So I'm going to take the camera off and show you the setup here. All right, here we are in the vent lab. We have two tripods. These are set up in the manner that we would have them set up. So this would be the upstream pitot tube, and then connected to the total pressure tap on this is a single line, which then goes to the manometer and is connected to the positive pressure tap on the manometer. And then vice versa, or conversely, this would be the downstream pitot tube, and its single tube from the total pressure tap is connected to the negative side of the manometer. So both of these are facing into the flow, and we'll just record a measurement, and then what we will do is we'll move the downstream pitot tube past the upstream pitot tube to the next measuring station. We will reverse the connections on the manometer, so this one will now become the upstream or positive pitot tube. This one will be the downstream or negative pitot tube, and we repeat the process going around the loop. Okay, so fairly simple, and with that background, let's go take some measurements.